Good morning, ladies and gentlemen. I'm Dr. Peter Pelumi Ikubanni. I'm from Bowen University, Nigeria. I'm here to present on this topic titled Sawdust Hash Reinforcement Impact on the Properties and Microstructure of Aluminum 6063 Matrix. These are the outline, introduction, aim, the methodology, results and discussion, conclusion, and references, if any. I As a way of introduction, composites are polyphase materials that consist of matrices and reinforcements which are developed to fulfill the demand of modern-day engineering construction demands based on their thermal properties and good mechanical characteristics, which include higher strength, hardness, toughness, and higher resistance to wear and corrosion. Now, engineering composite materials are part of advanced engineering materials, which are divided into metal matrix composite, ceramic matrix composite, and organic matrix composite, as seen in the slide 3. And under the matrix composite, we have the aluminum base, we have the magnesium base, the copper base, iron based, titanium based, and intermetallic compound based composite. While the organic matrix composite consists of the polymer matrix composite, the carbon-carbon matrix composite. However, we are concerned about the metal matrix composite and is the focus of this study. It consists of a metal matrix as the base material, along which the reinforcement materials is introduced into it. Now, there has been an increased demand for MMC in automobile, marine, and aerospace industries due to their enhanced properties. And in these, aluminum alloys are the predominant non-ferrous metal, which are used for these various applications due to their good strength to weight ratio, corrosion resistance, and heat and electricity conductivity. Now, several methods have been used in fabricating AMMC or MMC and are available as presented. So these are the various ways. You have the solid state, the liquid state, and the other techniques. And under the liquid state, which is our interest, we're looking at the stair casting. The stair casting method is our uh, focus in this study. However, stair casting process was used to develop reinforced matrix composite in this study. Stair casting procedure is one of the most commonly used techniques in the fabrication of MMC and most especially for aluminum matrix composite. The stair casting technique allows for uniform distribution and dispersion of the reinforcement particle with the matrix material, thereby granting the resulting composite good wettability and reactivity. Several reinforcements have been used by different researchers. For instance, graphene, titanium oxide, alumina, silica oxide, boron carbide, silicon carbide, and so on has been used as displayed in this figure. Those are called the synthetic ceramic reinforcements. Now, due to the high cost of these synthetic ceramic reinforcements, alternative reinforcement materials have been researched by several researchers, and hence attention has been turned to the utilization of agro waste or biomass and industrial waste and their derivatives, which are considered environmental waste. Some of these wastes include rice husk ash, the bean pod ash, palm kernel shell ash, bamboo leaf ash, fly ash, which is an industrial waste, red mud, and so on. These derivatives are hybridized with synthetic ceramics reinforcement to produce MMCs. So they can be hybridized, they can be used monotypically for the production of MMC, which is metal matrix composite. As seen in the other figures there, we have the concob and other materials being shown there. Now, Several researchers have employed different aluminum matrix composites which are being used across the globe, though new research work are still ongoing to discover more suitable compositions of reinforcement materials. However, little or no work has been done on the effect of sawdust ash, especially the thick wood, as a monolithic reinforcing particulate in aluminum matrix alloy for AMC synthesis. And that's why this topic is looking at these aspects for our research work. Now, the aim of this study is to evaluate the effect of using tectona grandis sawdust, which is the thick wood sawdust, as reinforcement on the physical mechanical properties of aluminum 6063 matrix composite. And some of the specific objectives of this work is to consider and evaluate the physical properties of developed composite, to assess the mechanical properties of the developed composite, and analyze the strengthening mechanism of the composite through examination of the fracture surface of the composite produced. Now, these are the materials used for this study. We have the sawdust ash from thick wood, the aluminum matrix, and their chemical compositions are displayed. For for interest, silica for table 2, silica, which is SiO2, is the required. It has the highest percentage, which is the required. Other elements, oxides, are also strengtheners that help to improve the property of the matrix inside. So this the figure 1 shows the method by which these materials are produced and to the extent of carrying out the results. So for material sourcing to sample preparation to sample characterization and result analysis. Now, this table 3 display the design, how it was designed. A naught designation means that it's the control sample, which the composition, the alloy matrix um, is not reinforced, it's an unreinforced alloy, while other ones are reinforced with 2%, 4 and 6% of the sawdust ash. And the sol after production using the stair casting method, figure 2 ensued, where we have the solid metal composite from the sand casting, and it was later machined to produce the tensor sample as shown in the figure 2b. And the experimentation carried out on this are to determine the density and porosity percentage, and density was determined using uh, Archimedes principle, and porosity was also taken. So for the porosity percentage to be determined, the theoretical density was obtained and the experimental density was also obtained, and the difference between the two was used to calculate the percentage porosity. We also determined the hardness test and tensor test and impact test following the appropriate ASTM standard. And lastly, the microstructural examination was carried out for the sample after production and for the fractured surface of the sample. Now, going to the results and discussion of this research, the SRD in figure 3 displays that of the unreinforced alloy and the alloy reinforced with 6% SDA. And the SRD pattern displays the various phases present in the EMC for the samples. It can be observed that the phase present are that of an aluminum cubic crystal system with only aluminum faces and peaks. That is for the figure 3A, the unreinforced alloy. The presence of these peaks aside aluminum in the reinforced composite was due to the introduction of the SDA particles. The elements at the peak of the SRD are strengtheners. Those are the silica, the titanium, and other ones, calcium. They are strengtheners. It can be observed that the diffraction peaks appear in a pattern that corresponds to a phase. of a good crystalline structure and support the fact that there was a proper mixing of the SDA within the matrix. The same micrograph I've seen in figure 4 displays uniform distribution of the SDA in the aluminum matrix showing low porosity, and this can be attributed to the stair casting route used in fabricating the composite, which allowed proper dispersion of the reinforcement. Now, for the density and porosity, table 4 shows the theoretical density and the experimental density. The theoretical density was determined using the rules of mixture, while the experimental density was determined using mass over volume, and these are the results obtained. And porosity was calculated by subtracting and taking it over the theoretical density to determine the porosity value as that. And from these results, the following can be deduced: that the density reduced with SDA addition in the composite, and this is due to the lower density of the sawdust ash compared to the aluminum. So the more the SDA in the constituent, while the aluminum is being reduced, the lower the density also of this. It shows that the reduction makes it possible for us to be able to produce a lightweight application using the stair casting method, and also the stair casting method is also a reliable method for producing or for developing AMC. And the variation in the experimental and theoretical density were majorly caused by voids and pores, which indicate some level of porosity in the composite, as seen in the porosity percentage. And the porosity percentage was within the acceptable range of 4%, as established by several studies like Alaneme 2018 and the likes, other several research. Now, it is good to establish that high porosity reduces the strength of the composite and depletes other mechanical properties. So with what we have here being within the range, acceptable range of 4% for MMC, it shows that the strength of the composite produced here is suitable for lightweight application as envisaged. Now, for the other tests, mechanical tests, hardness, tensile strength, and impact strength, figure 5, 6, and 7 displays respectively. The hardness and tensile strength of the composite, as seen in figure 5 and figure 6, increase with addition of SDA. This may be due to the presence of hard face and strengtheners of the SDA particles in the ductile matrix. An increase in hardness can also be attributed to the increasing reinforcement surface area and matrix grain size reduction as a result of addition of the reinforcement particle. And the increase in the tensile strength can be attributed to strong particle and matrix bonding interaction resulting from the uniform dispersion of the SDA particles in the metal matrix. Now, the thermal mismatch phenomenon between the matrix and reinforcement in terms of their thermal expansion coefficients is another good reason for the improvement of the composite material developed. Another mechanism that can be put in place is the Oron bypass mechanism that improves which is another improvement mechanism where there is a grain refinement of the matrix alloy as a result of the reduction in the grain size of the metal matrix to accommodate the reinforcement particle during the production and processing of the composite. The unreinforced alloy has the highest impact strength, and the impact strength reduces with increased SDA addition. And the brittleness of the SDA particle, even though they are hard, used for the reinforcement and fusion of voids in the composite could be attributed to impact strength reduction. So that's why the impact strength reduces due to the brittleness of the SDA particles. Now, this is the microstructure of the fractured surface after the tensile experiment, and from this we have for the first the unreinforced the 2%, which is the B, the 4%, and the 6% SDA reinforcement accordingly. Now, this was the this was done on the fracture surface. I mean, the macrostructural examination was done on the fracture surface of the tensile sample, as earlier said, and the crack propagation resulted into failure due to absence of reinforcement particle in the unreinforced matrix alloy. And the reinforcement particle have the tendency of reducing the crack propagation due to the material flow restriction, according to Yadav and Bowen 2011. Also, SDA addition enhances the plastic deformation of the composite, while the elastic deformation is reduced with increased load of composite. Better compatibility as SDA content increased in the matrix alloy. This could be linked to the increased hardness and tensile strength values of uh, the composite. In conclusion, this present study used environmental biomass waste derivative sawdust ash as reinforcement particles in aluminum 663 alloy for the development of monolithic reinforced composite using the stair casting route. The structural physics, microstructure, and physical mechanical properties of the developed matrix were investigated to determine the influence of SDA particles addition on the properties of the metal matrix composite developed. And from this, we could see that the SDA particles as reinforcement contain strengtheners in oxide forms, which strengthens the matrix when added. Homogeneous dispersion of reinforcements were achieved through the stair casting route, showing that the stair casting route is a reliable method of producing MMC. Density reduced with increased SDA particles, while porosity is less than 4%, which is the acceptable limit. And also, from the study, hardness and tensile increased, strength increased, while impact strength decreased with the addition of SDA particles. The SDA addition enhances the plastic deformation of the of the composite as reviewed by the micrograph. And lastly, the SDA is suitable for developing MMC for lightweight application, engineering applications. I want to thank you for listening to this presentation. Thank you.